Hey everyone, welcome back to the channel. If you have been working as a software professional for a few years, you eventually hit an invisible ceiling where just writing clean code isn't enough to progress. To design systems that handle millions of concurrent users without collapsing, you have to shift your perspective. Today we are kicking off a masterclass series designed to take you from writing code to designing at scale. Let's dive straight in. Before we start drawing arbitrary boxes and arrows, we need a standard mental model. What actually is software architecture at macro level? System design isn't just about picking a trendy database. It fundamentally boils down to four primitives. First primitives, your foundational compute, storage, and networking units. Second, contracts, the strict interfaces and communication protocols dictating how those units interact. Third, boundaries, your failure isolation domains that prevent localized errors from cascading. And fourth, evolution, your long-term strategy for system growth so you can scale without requiring a total structural rewrite. Every time you evaluate an architectural blueprint, you must force it to answer three core questions. Who must coordinate? What must scale under load? And what critical business logic must survive failure at all cost? If your design document doesn't explicitly address these three parameters, it's incomplete. This brings us to the fundamental five forces that shape every system topology: scalability, reliability, availability, efficiency, and manageability. If there's one thing you take away from this slide, let it be this. These are non-functional, macro-level system properties, not user features. You engineer for them from day one. Let's look closer at scalability. While vertical scaling has hard hardware limits, horizontal scaling introduces massive state complexity across distributed clusters. The golden rule of scale is simple. Scale fails at coordination points. Your bottleneck is almost never the physical network capacity. It is serialized coordination. The exact moments your data nodes are forced to stop, wait, and synchronize state. Next force, reliability. Here is the hard engineering truth. Redundancy is not resilience. Deploying three identical instances of a buggy microservice just means that you're replicating failures concurrently across multiple availability zones. True reliability is entirely about containment. You must map out independent failure domains and enforce graceful degradation so secondary services drop off long before the core transaction part dies. Then we have availability, which represents user perceived liveliness. Your system isn't available just because a monitoring ping says the server is technically healthy. It's available if an end user gets a valid response within a reasonable window. Maximizing uptime requires aggressively driving down your MTTR, mean time to recovery, using automated anomaly detection and self-healing topologies. And yes, this almost always forces a trade-off with strong data consistency. So let's draw a definitive line here. Reliability focuses on correctness over time. A reliable architecture might temporarily refuse incoming traffic just to defend its internal data states from corruption. Availability focuses on responsiveness now. An available system might willfully return slightly stale or out of order data just to keep the interface interactive. You must know which trade off your domain demands. To measure these forces in production, look to efficiency and manageability. Efficiency isn't tracking your average latency. It means monitoring your P99 tail latency outliers and establishing strict microsecond latency budgets across every single internal call hop. Manageability is your commitment to deep observability, metrics, structured logging, and distributed tracing. Because sustainable systems are observable systems. To close out this framework, let's look at the ultimate architect mindset. It's a clean four-part manifesto. Design for failure because everything eventually breaks in production. Minimize coordination to unlock true concurrency. Optimize the common path where 90% of your real traffic lives. And automate recovery because human response times are too slow for modern hyperscale. Systems fail at boundaries. Make sure yours are engineered correctly. That wraps up our baseline architectural framework. In the next chapter, we are getting hands-on with the first real system component, load balancing. We will break down exactly how to distribute load equitably, preserve P99 latency targets, and prevent total backend cascade collapse. Drop your design questions in the comments below. Hit subscribe so you don't miss the next deep dive, and let's keep designing at scale. See you in the next one.